Our next speaker, Tzachi Cohen. Tzachi is a member of the technical staff at AMD. He is part of the HSA software group and has been leading the integration effort of HSA with the existing software stack.
I made my introduction. Okay, so just so I can adapt myself to the audience, how many of you have ever made some hands-on GPU programming? I would say about a third. Okay, so this is exactly what at AMD we are trying to change. We know today that programming to the GPU is difficult. We have a whole company that specializes at helping people with programming to GPUs. And we are trying to make programming to the GPU more simpler and more CPU-like. And how are we going to do that? So 2 years ago, AMD incepted a standard called HSA. We created it, but many companies joined in, and we created a consortium. And HSA is a system architecture comprised of requirements from the hardware and API to be implemented by the software. And its main purpose is to bring together 2 or 3 different breeds of processors and make them work seamlessly together. So in the AMD case, or in the APU line of products, the 2 breeds of processors are the CPU and the GPU. We call the CPU the latency compute unit, because due to its characteristics, the CPUs have relatively low latency when responding to inputs. It's very good at serial workloads. It has very good branching capabilities. But when it comes to throughput, the GPU is actually the winner. However, the GPU has its own shortcomings. Its ability to perform branching is poorer. And it takes time for the GPU to respond. If we, for example, enqueue some workload to the GPU, it takes about 50 microseconds from the time that we enqueue the work until the driver processes the kernel that we just launched, until something happens with the hardware. And we like to take the best of both processors and make them work together, and finally make the programmer more in control of what's happening, and make this entire task of incorporating the GPU into your program much easier. So today, the latest, the first HSA compliant chip that AMD is manufacturing is called Kaveri. It's an APU, accelerated processing unit. It is a chip with a GPU on die and a CPU on die. We have 4 CPU cores on it and 8 GPU compute cores on it. And as you can see, the chip can reach about 850 gigaflops per second. 118 of them are CPU, the capability of the theoretical peak of the CPU, and 730 are the theoretical peak of the GPU. Now, we incorporated into this chip quite a few features that would make the GPU a first-class citizen in the SoC. And what do I mean by when I say first-class citizen? First, it has, we call it HUMA. The GPU has full and equal access to the memory as if it was the CPU. And when I say full access, I mean several things. First, the GPU has full 64-bit access to the entire address space of the CPU. Well, 64-bit is not exactly 64-bit. As we all may know, 64-bit systems are actually 48-bit systems. Okay, that's enough for any earthly use, and we use less bits just to save silicon and power. The GPU has full 64-bit address, space access, and it has the same bandwidth to the memory as the CPU. It actually has even a slightly higher bandwidth to the memory compared to the CPU, and that makes it that gives it an advantage compared to discrete GPUs that has to access the system memory through a PCI Express bus. That even if it is a PCI Express Gen 3, which is about 15 gigabytes per second, we still have a serious latency because of the PCIe protocol. You have to transmit a read packet and then receive a read result. It takes about 100 cycles at least for the GPU to have any transaction through the PCI Express bus. Last but not least is to kind of change the dynamics between the CPU and the GPU. GPU traditionally is regarded to as a coprocessor, a slave coprocessor, a passive coprocessor that does whatever it is asked from. It is asked for. And we decided to say, okay, if the GPU is an equal citizen, a first-class citizen, then traditionally the CPU enqueues work. Once we launch an OpenCL kernel, for example, the CPU enqueues work to some GPU queue, okay? And the GPU processes it at its own time. Now we allow the GPU to enqueue work back to the CPU, and the CPU would process it when it has idle quantums. The rationale behind this dual architecture is that we have tasks that are very branchy, that we'd like the CPU to compute, and we have tasks that are massively parallel and suitable for SIMD, SIMD architecture, and the CPU queues those works in the GPU queue. So the work queuing is bidirectional. So as I said earlier, Kaveri is our first APU, accelerated processing unit, that is full HSA compatible, and it has also compatible with OpenCL 2.0. And today I want to speak about, I'll give 4 examples of how those brief features that I just described are helping to solve real-life problems or real-life issues that we encounter when we do GPU programming. We speak about data pointers. We speak about platform atomics, which I'll elaborate in a short while. We speak about how to access large data sets. And we'll speak about the GPU being able to do CPU callbacks. So data pointers. So traditionally, the CPU, let's go back to how the CPU translates virtual addresses to physical addresses. If we all remember operating system course, then the CPU has a set of page translation buffers that take from one end virtual address and produce on the other end a physical address. The CPU memory controller can access only physical addresses, and that's how the translation is done. The GPU, had its own separate virtual address space that it is abstracted by the programmer with the current programming model, CUDA or OpenCL. The programmer doesn't really know about it. If the programmer is allocating a chunk of memory on the GPU, most of the time he doesn't even know what is the GPU virtual address. And those two translations live in 2 separate worlds. What we implement in HSA is the GPU being able to page walk the CPU page translation buffers. So we have one coherent uniform memory address, and this requires some operating system support, but it works. And the question that arises, what is it good for? So let's take the example of traversing a binary tree. Okay? So traditionally, we have a tree, and we like to perform some walk in it. In order to make the GPU perform the binary tree traverses, then First, we had to nest the tree on some contiguous buffer. And instead of using pointers from node to node, we used indices from node to node. And now indices are not virtual address dependent. We can use indices in CPU space, and we can use indices in GPU virtual address space. And there was no conflict. And then we could write code that would access the GPU virtual address space without even knowing about it. Okay, so we just nest all the nodes in a contiguous buffer. This buffer is somewhere in GPU memory. Then the GPU would walk using indices the tree, accumulate the result in some kind of buffer, copy the results back to system memory, and the CPU could pick it up from there and continue the computation. This obviously included a major overhead. With HSA, we said that we have a unified address space, so the GPU just dereferenced any pointer transferred to it from the CPU, and it performs the walk as if it was the CPU, and delivers the results directly back to the CPU. This saves us a few things. First and foremost, code. We don't have to write the code that copies the data to the GPU. We don't have to invent the code that nests a binary tree on a buffer. We don't have to copy the data back. That's the first thing. We have simpler programming model. The second thing is that we save power because we make redundant the memory transfers, and memory transfers take power. And the third thing is performance. If we do not transfer data redundantly from side to side, at the end we get better performance. This is the result that we produced at our research lab. The cyan columns are single CPU results. As you can see, we do about 4,000 node traversals per second. With a quad-core implementation, we reach about 10,000 to 15,000 nodes per second. And when utilizing the massive parallelism of the GPU, we can reach almost 50,000 nodes per second in a binary tree search. Okay, platform atomics. So I said earlier that the GPU has equal access to memory as the CPU does, and I mentioned that it has access to the full address range of the CPU. It has the same bandwidth. What I didn't mention yet is that the GPU also has the ability to perform coherent atomic operations that will be coherent to the CPU. And that is very strong because now we can implement all kinds of patterns that would be CPU-GPU coherent. For example, we can perform fine-grain producer-consumer between the CPU and the GPU, and the CPU can queue work to the GPU while the kernel is running. Traditionally, when the CPU was queuing work to the GPU, it would usually have chunks and wait for the results only when the kernel execution is ended and then queue some additional work. Now the CPU can just perform atomic operations on some read pointer and write pointers or consumer and producer variables, and the GPU would see it coherently. Another example that we can, another use case for atomic operations that are coherent between CPU and GPU is the construction of a binary tree in parallel. If we look at the legacy, if we try to perform a binary tree construction in the traditional or the legacy programming model, then the GPU would basically do all the work. We'll have some input for the GPU, and the GPU has internal atomic operations. It can, in parallel, build some kind of tree. Once we have atomic operations that are coherent between CPU and GPU, then we can make, and we have a unified memory address, we can all build the tree in parallel. The CPU can build several nodes, both CPUs can build several nodes, and the GPU can build several nodes as well. Large data sets. Okay. So let's assume for a moment that we have some kind of gigantic database. Let's say 40 gigabytes of database. Now, this the kind of database will not fit in the GPU memory. GPUs usually ship today with with an average of 3 to 4 gigabytes. Some professional GPUs have, I think, 10 gigabytes, but that is the upper limit. When the GPU has equal access to the system memory, which can be huge, we can have 64 gigabytes of actual RAM, then we can access any huge database as is, without any consideration to the GPU being limited with its dedicated video memory. For example, okay, with OpenCL 2.0, HSA is a general purpose interface. We intend for many parallel programming interfaces to be implemented above it. We designed it in such a way that OpenCL can be implemented above HSA. C++ AMP, that's the Microsoft technology for parallelization, can be implemented above HSA, and OpenMP as well. With OpenCL 2.0, we have HSA features exposed through the OpenCL interface, mainly the shared virtual memory extension. So with HSA, we just, let's say we have big database, in this case an octree. Let's roughly divide it to 4 stages, 4 levels. That's not necessarily correspond to direct levels of the tree, but let's say that 4 levels that are more or less equal in size. So with the GPU, we can just access with the reference level after level as if it was the CPU. On legacy implementations, we had to copy chunks of this big database into GPU local memory and iteratively traverse the database in chunks so it would fit inside the GPU local memory. In this instance, if we have five levels, then we'll then copy just the first upper 2 levels that would fit inside GPU memory. We'll do the first traverse. We'll save the intermediate results in some buffer. And then we'll launch a second kernel to access the lower levels of the tree. Okay? And save it in some intermediate buffer, and then we'll just copy a different subtree of the graph into local memory and traverse there until, well, in this instance we have about 64 chunks of this huge database to copy back and forth into GPU local memory, just to be able to traverse it in its entirety. Of course, memory transfer can be overlapped with kernel execution, but the overall performance and the complexity of the code, it takes a considerable effort, which with HSA is redundant. Okay, CPU callbacks. Another interesting feature that is coming our way. As I said earlier, we have 2 breeds of processors, each with its own strength. And sometimes we encounter a task that requires the conjugation of both processors. For example, let's say that we have some video image, and we would like to extract chroma and luma values from the image. Now, moreover, after we extract those values, we would like to further process tiles in the image that pass a specific luminance threshold. Now, we know from starters that only a very small percentage of the tiles that are in the image are going to pass this specific threshold. And the question arises, how can we efficiently implement it using HSA? So what we can do is we can run a kernel, launch a kernel, and whenever we do some initial processing of all the chunks that are very suitable for GPUs, because this is a very parallel and non-branchy code to extract luma values from pixels. And once we have a specific tile that passes a specific chroma luminance value, then we just, as I mentioned earlier, queue the work to the CPU and have the CPU perform the branchy code of painting the tile in red to specify that this specific tile is too bright. We definitely could implement the same thing with a legacy implementation. However, we will have some GPU underutilization because we are running branchy code, and then some parts of the SIMD are going to be underutilized because they are shut off, because for the specific tile they are responsible for, there's nothing to do. Okay, we're good with times. Okay, so those are a few features or few use cases that are suitable for HSA. We also care a lot about the ecosystem and the ability of the developer to exploit and to harness this power. And we have a lot of engagements into the community, and we have elaborate about what we do to better enable this power and to make it tangible to developers. First and foremost, we are doing a lot of effort to integrate GPGPU into Java. We know that OpenCL developers are unique, but ultimately they are a very small portion of all the programmers out there. Most of the programmers out there, well, don't catch me in my tongue, but a large portion of the programmers out there are Java programmers, and we would like to make it simple for Java programmers to be able to access the GPU to accelerate computations. Currently, we have an extension to Java called Aparapi, which is simply an OpenCL binding for Java to enable Java developer to easily access the GPU. Later on, with Java 8, we'll have Lambda APIs, which will enable the programmer to write Lambda expressions and compile them and bake them into GPU code. And later on, Oracle themselves are picking up the call, and they intend to launch a Java Stream JDK to make it cross-vendor and cross-product to enable Stream SDK officially inside Java. Also, we have the AMD APP SDK, accelerated parallel processing development kit, which has many samples and tutorials on how to use OpenCL. We have the MEDI SDK. Well, some HSA partners are not trying to bring together only CPU and GPU. They try to bring together a CPU and a DSP, and a digital signal processor. So actually, AMD GPUs also have a few digital signal processors on them themselves. We have a video encoder and a video decoder, and we have the ability to decode video, run some OpenCL processing kernel on it, and decode it back and do it all on the GPU. So we have a media SDK that unleashes all the nice features that we have with video encoding, and we intend to have a unified SDK for both of them. We have AMD CodeXL, which is our unified debugger and profiler. It has a client for Linux. It has a client for Windows. It comes in the form of a plugin for Visual Studio 2010-2011. This tool is actually, most of it is developed right here in Israel, and it's free. You are welcome to download it for free in under a few minutes and just install it and run it. It has OpenCL step-in debugging capabilities, which makes OpenCL kernel debugging very similar experience to CPU debugging. You can just place a breakpoint on your code and debug within the Visual Studio IDE or within the client, the standalone clients. We have inside it, that's new to version 1.3. We have a static kernel analyzer or shader kernel authoring tool. You can write your own kernels offline and compile it offline and quickly sort out through all the compilation errors without running your program, which is sometimes very, very convenient for developers. And we have a rich set of complementary library. We have some implementation of OpenCV above OpenCL, not the entire package, but a few central functions that are implemented with OpenCL. We have Bolt that makes programming to the GPU very close to STL-like code. We have CLMath that performs basic linear algebra routines and fast Fourier transform on the GPU. And we have the Upper API that I mentioned earlier. And that's about it. Any questions? Yes?
You mentioned that the GPU can access the system memory. Does it also have a dedicated memory, a dedicated separate memory?
Yes. We have to bear in mind that the GPU is actually still responsible for graphics, for running DirectX, OpenGL, and so forth. So in addition to the GPU being able to access all the CPU memory, it has its own dedicated memory mainly for graphics, and it can use this memory for OpenCL as well, or for HSA as well.
You mentioned that CPU and GPU can pass processes back and forth. Who manages this, the operating system, or it's directly managed by the CPU or something further?
So yes, definitely for the GPU to access a CPU pointer, it sounds simple, but trust me, it doesn't. You really need operating system support for it. And we have a driver that implements it without operating system support, but we already have operating system support in Linux. Linus Torvalds himself submitted the code for supporting external devices trying to reference CPU pointers. The device that does it is called IOMMU, and it can access through this device. The GPU can access the memory to the system.
I'm asking is who is making the decision when to send the process to the GPU and not to keep it at the CPU.
So
when to make it randomly.
So the decision is not opaque. The GPU cannot just take x86 code and run it without the programmer's intervention. The programmer still has to write kernel or has to write code that will specifically and explicitly run on the GPU. However, the same way that OpenCL works. However, there are very, very fewer limitations to how this code can access memory.
But I'm asking, same way today you have several cores on CPU and the operating system decides how to distribute processes between the cores. does it handle the GPU as another specialized core and just ship some code that it deems appropriate to that, or the code has to be written specifically to call for a GPU to?
Well, the code has to be specifically written to the GPU. Having said that, the GPU has several entry points. It has several queues. And every process can connect to a different queue. And the GPU itself can run in parallel kernels from several processes. And it has a specialized hardware scheduler that knows to load balance between different processes solely on the GPU side. Yes?
What's the latency? Suppose there's just one process that the CPU puts in the queue for the GPU or vice versa. Nothing else is happening. How long will it take from one saying, okay, go, to starting the first instruction?
On average, between 30 to 50 microseconds.
So it's still the equivalent of tens of thousands of instructions.
Correct. Yes.
In a multi-node system, who issues network instructions? Does it have to be done by the CPU?
What do you mean by network instructions?
Let's say one API code.
Okay.
Or only on the CPU, or can I get that into the GPU?
Well, they will definitely say this is that would be a very nice research topic. Yes.
What's the current bandwidth on the AMD architectures from the GPU to the memory? I remember that it used to be much lower than GPU access, than discrete GPU.
Well, it really depends on the chip and exactly the configuration of which exact flag you used when creating the resource. But it's between 15 to 20 gigabytes per second.
So it's still way lower than discrete.
It's still way lower than discrete, but you need to bear in mind that the integrated GPU on the APU is also way smaller than the monster we have on discrete.
Thank you very much.